Yeah, if there's anything you want to ask a question about, got it, or you could just tell me now. Silence is deafening. You have.
Can you go over, like, for some related problems with calculus and then your linear approximations?
Related rates, linear approximation. Someone else, yes? Critical points. Optimization. Anything else anyone wants to, you can change your mind later.
You also there's like points of inflection, at least how to find them.
Points of inflection. Okay. Yes?
Yeah, let's go over it.
Everything. You want me to go over hyperbolics? All right, I guess what I need is, okay. I'm going to leave this up here. We'll just go through all of it, but we're going to have to do it on this piece of paper over here. I mean, this board over here. Okay. So, related rates. Let me do a simple related rates problem. Say you have two values, a plus b, and they're equal to 12. And you want to maximize. This is not a related rate problem, this is an optimization problem. Related rate problem. Okay. I think I did this on the last semester, did an exam like this, problem like this, right? You have a triangle, and I give you, it's an equilateral triangle. And they're nice about it. I didn't make you do the geometry on the exam, but the area of this equilateral triangle is what? So it's the base times the height. What's the height? 1/2 s squared 3 2s. So it's times square root of 3 over 2s, but half of that because it's a triangle. So it's square root of 3 over 4s squared. And s is increasing at 10 centimeters per minute. And the question is, how fast is the area increasing, when S is 20 centimeters. Okay, so you want to picture this in your head. You got a triangle. The sides are increasing at a nice speed, slowly. And the area is increasing, but the rate the area increases varies, but it's related. It's related to the rate that the sides are increasing. So almost all these problems begin with, well, you have to find in this case, I give it to you. You have to find something, some formula that connects the area and the side. But now we need to know how the rates related. And invariably, your best bet is to think of the chain rule in this form, where dy dx equals dy du dx. Now, yx and u can be all sorts of things. So then you have to figure out how to apply this to this problem. So here we have the area dt. That's what we want to know, right? How fast is the area increasing? So what else do we know? We know S and, well, we know ds dt because we're given that. S is increasing in 10 centimeters per minute. So we've got this. We need this to get this. All right. That's the way to look at these things. Even, the problem can be completely different. It can be a ladder sliding. It could just be some numbers changing. So dA ds. Well, we have the area in terms of S. So it's just a simple derivative. So what do we get here? We get square root of 3 over 2s. So filling this in, we have square root of 3 over 2s times 10 centimeters per second. That's our change in area with respect to time. But the question asks, how fast is it increasing when s is 20? So you just plug in 20 for s. So what do you get? 250 times the square root of 3 centimeters per second. Centimeters squared per second. Because s is in centimeters. Aside from going over the homework problems, making sure you see how those work, so you have a little variety of things. I really try hard not to give you some complicated geometry problem that nobody's ever going to, figure out during an exam. Probably figure it out. Created a little committee and get to work on it for a few hours. Maybe you get it in 5 minutes. It just depends. Okay. Questions about related rates? Yes.
Would you give us like the formula in the area if it's like a circle?
Probably. I mean, just it's a practical matter. Like if I have some rectangle, you know how to find the area of a rectangle. Hopefully, it's like a brick. Parallel pipe it. Hopefully you know how to find the volume. And if it was something even like a sphere, which I hope you would know by now, the volume of a sphere is 4/3 pi r cubed. I would probably give you that. And if I didn't, and you made something up and it was wrong, but you got everything else, you just get a few points off. Because I want to know if you can do a related rates problem, not if you were in Eastern geometry 3 years ago.
You'd also give us like the trapezoid. You give us like the geometry part, like the area of like trapezoid or whatever. No matter what shape, it doesn't matter if you just put it on the exam.
Trapezoid. Base 1, base 2, height. Area is base 1 plus base 2 over 2 times. You mean like that?
You throw that on there? Or?
Michael, I'm sorry. I just gave it to you. I'll give it to everyone else, but it won't be on your exam.
No, I write it down right now.
You can write it down. You get a cheat sheet, right? You can write whatever you want. Write all the things that you you think you want to know? All right. Other questions? Other questions on related rates? I will say this is one of the subjects where there's nothing I can do to automate it. You're going to have to, leave that problem for the last, so you have plenty of time. And you're going to have to, relax and use your creativity. Not everything in math is just a formula. All right, erase this now. Did you get everybody? Keep finding people sneaking in without me noticing. There's another person. Okay.
I'll do the function return area. That's why I was on those. That's the key. You have to make that vote and just get to it.
Oh, okay. I think I have some. Okay, an update to Adobe. No, thank you. Okay, how to do linear approximation calculation. So, just as a reminder, the idea is we have some curve. There's some point that we know the function. We have some point, we'll call it A, and we know the value at A. And we want to find something that is a little off from there. And so we use the idea that the tangent approximates the function close by. And so f of A plus h is going to equal f of A plus the derivative in A times h. I noticed the book writes it a little differently. The f of x equals f of x plus h plus a f of a plus, we'll look it up. There's a different formulation which might be more useful. All right, so how does this work? Well, I mean, I suppose if you're on a desert island without your calculator and you're trying to figure out what the f of x equals x cubed, and you want to know what f of 3.1 is, approximately. So you think of this in terms of, well, and I'm assuming you're really, really bad at math. You can't like cube this. It's too much trouble. So this is 3.0 plus 0.1, which, again, I want to be clear, this is an approximation. Well, that's going to be f of 3. Well, you know what that is. That's 27 plus 0.1. Well, we need the derivative now. F prime of x is 3x squared. So this times 3x squared, where x is 3. times squared. So what's that? 27 times 0.1, 2.7, so 29.7. I don't even know if that's a good approximation. But that's the idea. If you're close to some point, you're just some little delta away from it, and you use a linear approximation to get from somewhere you know. That's what they want you to do with these problems. They can be used whether you have a nice number here or not. It comes up in some numerical calculations where you're going to need to know this approximation. So, all right, got it. Look at the homework, look at my problem, that's what you need to be able to do.
I have a question.
Yes.
So you see how in one of the parentheses you wrote 3.0 plus 0.1? Do you see how in one of the parentheses you wrote 3.0 plus 0.1?
Yeah.
What if, let's say I wrote like 2.9 plus 0.2, like will I get the same result?
You know, it's a combination of the mask, the echo in my hearing. Just say it a little louder and I'll get it.
Okay, so you know how in the parentheses, right? You wrote 3.0 plus 0.1.
This?
F of 3.0 plus 0.1. Third line, above, at the start, toward like the left side.
Keep going. There you go.
Oh, well, you see, I'm trying to break this value 3.1 into something I can calculate easily.
Yes.
See, 3 cubed is, I know is 27. That was the point in doing that.
But if I like broke it down to like 2.9 plus 0.2, will I still get the same result at the end of the day?
No, you won't. You'll get a different approximation. And because 0.2 is further away than 0.1, it'd probably be a worse approximation.
So then how do we know like what's the perfect approximation?
Yes, this is the problem with teaching a linear approximation in this class. You could argue, well, why not make it 3 point, I don't know, 3.09 plus 0.01, right? Yes, that would be a better approximation, but it removes the ability to figure this out simply. If I can figure this out, I can figure this out, right? I can cube this, I can cube this. So this is the example we have at this level. It's not a very, it seems kind of, wow, I got a calculator. Right? That's totally legitimate.
I think the book had one that was like 1.999, so you could just use 2.
Yeah.
Yeah, well,
So like arbitrarily.
f of 2.000 minus 0.001, that's f of 1.999. Is that what you mean? And don't forget that here you've got a minus, so over here you're going to have a minus.
Yeah, it was like 32, 1.999 minus 2 plus 16, and it ended up being like 15.968.
What was the function on that problem?
X to the 4th.
Okay, let's do that.
The number was 1.999 to the 4th.
1.999 to the 4th. And this is to the 4th. So the derivative is 4x cubed, right? So instead of finding f of 1.999, we're going to find f of 2.0, right? So linear approximation tells me this is approximately f of 2.0 minus 0.001 times f prime of 2.0. So all right, let's figure out what that is. f of 2 is 16 minus 0.001. What's this? 32. So it's 16 minus what? There's my approximation. Again, one can argue what's the purpose of, actually doing this problem. It's not a real world problem because you would just have a calculator. The purpose of this is to show this linear approximation and how it works. And then, when you're doing, I don't know, biology, physics, some science, or maybe in computer science they'll come up because they'll dispute it. They might be asking you to use a function where you're not actually able to calculate it this way. You might have some data points and you use some smooth, approximation of that function. And this allows you to, extrapolate from a particular data point. So, if I'm not sounding as enthusiastic as a math teacher should be about this, it's because it isn't on my list of important calculus things. It's just on the curriculum I need to go over. So, all right. Any other questions about? It's just something you need to understand hopefully understand what's going on, and then you just be able to use the formula. Okay, any questions about this one? All right. Do I need to talk about hyperbolic functions?
Can you go over the four examples?
What is the derivative of the hyperbolic tangent of x? Well, the hyperbolic tangent is the hyperbolic sine of x over the hyperbolic cosine of x. You might actually just happen to remember what it is, and that would be okay. But here we have to use the what rule? Quotient rule. We haven't forgotten that. So derivative of sine h of x times cosine of x times cosine x minus derivative of the cosine hyperbolic times, you can't fit it, all over cosine h of x squared. So the derivative of the hyperbolic sine is this is like the easiest, if you remember, it's easy. Derivative of the hyperbolic sine is the hyperbolic cosine times the hyperbolic cosine squared minus, again, now we have the hyperbolic sine squared over sine h of x squared. Now, at this point, it would be handy to know that this is an identity. It's like the Pythagorean identity, but it's for hyperbolics. Hyperbolic cosine squared minus sine squared, hyperbolic sine squared is 1. So this is 1 over x squared, which is hyperbolic secant squared. And you wouldn't actually have to get to here. If you got to here, I would be fine. Maybe it helps to know that the hyperbolic sign is equal to e to the x minus e to the minus x over 2. So if I want to find the derivative, well, that's going to be e to the x minus e to the minus x times minus 1, so it becomes a plus. And this is just the hyperbolic cosine. Might be helpful to know that. Put that on your cheat sheet. Okay. Yes?
Can I ask why it's minus sine h x squared and not plus?
I'm sorry?
Can I ask why it's minus hyperbolic sine x squared and not plus?
Well, this minus comes from the quotient rule.
Yeah, and the derivative of cosine is negative sine?
Yes, but the derivative of the hyperbolic cosine is the hyperbolic sine.
Okay, so it's not negative.
They're not the same as, so. You can figure this out with those definitions in terms of e to the x. But let's take a look. If the hyperbolic sine is e to the x minus e to the minus x over 2, its derivative derivative here is e to the x plus e to the minus x over 2, which is the hyperbolic cosine. If I find the derivative of this, it becomes e to the x. This is going to introduce a minus e to the minus x over 2. Back to the hyperbolic sine. So it's not the same as sines and cosines, trigonometric sines and cosines. You know, it's just derivative, derivative. You should know that. This is a really useful function for that reason, because if you have, I know this is jumping way ahead, if you have a differential equation where the second derivative of a function is equal to, say, some constant times the function, you think to yourself, well, what function do I know whose second derivative is some constant times the original function? Well, these should come to mind. Anybody going on in physics, biology, chemistry will need to probably take a differential equations course, and then it comes in handy. Shall I go on? Number 4. Is it okay? I'm running out of, I forgot my markers, so I'm going to have to change over to blue. So what's a critical point? Anybody remember the definition of a critical point?
A point where the derivative is equal to 0.
That's the first half. There's an or where the derivative is not defined. Okay, guessing game. So one more try at it. Full point. Derivative is equal to 0, or derivative is undefined. So let's say I take, I don't know, I'm going to do something simple. I'm going to say f of f of x equals, I'm going to do x squared minus 4 on the interval minus 8 to 8. Critical points are points where the function might have a maximum or minimum. And if it has a maximum or minimum, it might be the absolute maximum or minimum. So, what are the critical points of this function? Well, derivative is 2x. Where does 2x equal to 0? X equals 0 is a critical point. But I said on this interval, and on the endpoints, it's not differentiable. That's because that limit, we try and find, use the derivative function on this. There's no limit at the endpoints. So x equals minus 8, x equals 8 are also critical points. Now we can plug them into the function, all right? At 0, it's minus 4. Minus 8 is 60. And at 8, it's also 60, all right? So now we have some points to choose from. We can use the second derivative test on this. We can say the second derivative is 2, which is positive, so this has to be a minimum. And these are clearly their maximums.
Professor,
Yes?
did you plug the negative 8 into the f of x equation?
Yeah. 64 minus 4.
Okay.
So what does this actually look like? Kind of looks like this. And then this is negative 8, and some point here is 8. So we have these 3 points. And you can see this is the absolute minimum. These are both absolute maximums. That's what you do when you're looking for critical points. You look for where the function is 0 or where it's undefined,
So,
where the derivative is undefined. Yes?
so whatever value you get, that's what you choose from, because we got that x equals 0, and we had the closed interval -8 and 8. And so you plug those into the equation, and whatever is the lowest is what you count as the minimum.
Yeah. Now, you could, if you had some rational function, right, you might, your function might do something squirrely, like, zoom up, right, at some point. And then, you have to look at the function and see that and go, oh, it has no absolute maximum, because these things go off forever. I mean, it's not all just, straightforward. You have to kind of use your brain. I guess I probably should have said -7, and that would have been 45. And then this would have been only absolute max, and this would be only absolute. That's a better problem. Oh. I hate you, US Tech Department. You're not allowed to just be logged in. Okay, how to use the first derivative test to find if a critical point is a maximum or a minimum. let's see if we can use this. The first derivative test says that, what? If a point, like let's say we were to go from f minus 1 to f1. This isn't, in this case, it isn't necessarily the best way to do this because we can use the second derivative test. Well, if we look at negative 1 and 1, what happens? We get 1 minus 4 is minus 3, and 1 is, we're not going anywhere, are we? Oh, well, no, we want to know the first derivative. Gosh. First derivative is negative 2, and it's going to positive 2. So that tells us that as we go this way, the slope goes from a negative number to a positive. So that tells us this is a minimum. That's the first derivative test.
Plugging it into the first equation or the second?
The derivative. It's the first derivative test. So if the derivative goes from negative to positive, it's a minimum. Goes from positive to negative, it would be a maximum. And if it stays the same, it didn't help. You have to dig a little deeper. You can get functions like x cubed, where you have a critical point here. The derivative is 0. But on either side of it, here it's going from positive to positive. And in fact, it's neither a minimum or a maximum. You okay? All right. Stop me if you want me to stop. How to find points of inflection of a function? Okay, someone asked this earlier. So the way you find points of inflection, well, first, what is a point of inflection? Well, you want a kind of a graphical idea in your mind. You have a function that is curved down, and then at some place starts curving up. And where it changes, that's the point of inflection. I hope my diagram is clear. This has a curvature which is down, and over here it has a curvature which is up. So if you saw a picture, you'd know that that's where the point of inflection is. But if you have the function, it's where the second derivative is 0. That's where you may have a point of inflection. Now, coincidentally, I saw a question on Quora. You can follow me on Quora if you want. Read a bunch of junk. The question was, what are the points of inflection of this function? Actually, it wanted to know where the critical points and the points of inflection are. So, all right, the derivative is 4x cubed is equal to 0 at x equals 0. Second derivative is 12x squared, which is 0 at x equals 0. This is where you might have a critical point, a point of inflection, but you don't. Look at the graph, and it looks like a parabola. And what happens is the derivative gets to 0. The rate of change that the derivative is changing gets to 0. That's the second derivative. But it goes from what? Goes from negative to positive. So curvature is always in the same direction. So this is not really a point of inflection. Just keep in mind, take a look at the diagrams. This is where, it's down or it's up. Here it's just up. So, just something to know about inflection. How to use the second derivative test. I think we did an example, right? If it's positive, that means the derivative is going from negative to positive. So if you're at the point where your derivative is 0, your second derivative is positive, it's a minimum. And vice versa, if the derivative is, did I do that right? It's negative going to positive, that would be positive. It's positive going to negative, that would be negative, and that would be a maximum. I can't remember these things on the fly. I have to kind of dyslexic geometrically, so I have to think it through. You can write it down or think it through. Anyone want to hear about how to apply Rolle's theorem and the mean value theorem? So, helps to know what. I think I'll just deal with the mean value theorem. It's the Rolle's theorem. I can then just point out how it's the same thing, only simpler. Mean value theorem. So there's 3 parts. Well, wait. Mean value, there's 2 parts. One is the function is continuous on some closed interval. 2, it's differentiable on the open interval. That's just the minimum, it could be, if I give you a function that's continuous everywhere, on any interval this is true. The mean value theorem says that if these 2 are true, that there exists some c such that the derivative at c is equal to f of b minus f of a over b minus a. So what does that mean graphically? You have some function. You have 2 points, A and B. And if you find the slope of the line between these 2 points, that's this. That's our m. This is our slope. Then because this is continuous and differentiable, there must be some point here, some c, with the same, where the tangent has the same slope. Or if you like geometrically, it's parallel to this line. So what can you do with that? Well, I guess I could say, take the function f of x equals x squared plus 1 on the interval. I'm making this up, it may not work. On this interval, -1, 1. Now let's make it 2. Be more exciting. So, using the mean value theorem, show me what f prime of c is such that is equal to the slope of, how do you say this? F of 2 minus f of minus 1, or 2 minus 1. I mean, I can say, prove to me that there is such a C. Right now you can ask what it is. Well, you would go, well, wait, f is continuous, because it's continuous everywhere. It's differentiable. It's differentiable everywhere. Therefore, by the mean value theorem, this C must exist. That's the proof of the mean value theorem. Now I can say, well, what is C? Well, f of 2 is 5. F of minus 1 is 2. And this is 3. So it's 1. So what I want to know is what the derivative, derivative is 2x, where it's equal to 1. The answer is at a half. The only thing that Rolle's theorem would add to this is that for Rolle's theorem we say f of a equals f of b. That's the condition for Rolle's theorem. And Rolle's theorem tells you that there's some C where the derivative is 0. So if I ask you to use Rolle's theorem, you first have to check that f of a is equal to f of b, and then you could again find me some point where this is, it would look like this. Maybe like this. And this would be A and B, and f of A would have to equal f of B, and then there's some point C where the derivative is 0, where it's horizontal. All right. I'm not going to be able to explain number 9 very well. However, let me at least give you an idea what's involved. So I give you some function, and you look at the function and you say, oh, well, f of 1, I'm going to finish this up. F of 1 equals 0, and f of 2 equals 0. So that tells me 1 and 2, the function goes through these points. So then I look further and I find, well, we find that down here, let's say f derivative of 0 is some positive number, and derivative at 1 is a negative number, and derivative at 3 is a positive number. So now I know that the function kind of goes up and then comes down. Wait a minute, that's not right. That here it's increasing. Oh, here it's decreasing, and then at 3 it's increasing. I guess that's it. And then if I find out where the derivative is 0, those are going to be points where it's probably more like this, where the max and mins are. And then you can use the second derivative to find, is there a point of inflection along here? I think there's some homework problems along those lines, so you might want to go back and look at those. I don't know if I said this before, but if you look in the file section on Canvas, I put all my answer sheets. So you should be able to, like, if you're not sure about the homework, you didn't do something or did something wrong, you can go back and look at it. All right, we'll finish these up after the break. And we'll go through more. I think someone asked me if I had office hours today. Okay. So after class 12 to 12:30, I'm going to a lunch, and somewhere between 12:30 and 1, I'll be back in my office. Is that going to work for you? No. You want to see me right after class?
That would be great.
Oh, Or do a Zoom some other,
Oh, definitely,
you want to do that? Send me an email, we'll set it up.
Thank you.
Yeah, everyone's welcome to do that. I'll be around most of the weekend, so if you send me an email, always do Zoom. So, bring it back. Oh,
I just
yeah, I don't think
remember
it's-
Oh, okay, but I'll do that. Usually just one letter, or sometimes like one letter comes up twice. Like comma, I would have been get that at all. You know, I was like, I have like, of course I live in the UK, but they're like, it's right. Both of them, my son was last night, I was thinking, I had to write them down sometimes, because I didn't really want to get them. But,
So I have the wrong word here on the sheet. It says what an indefinite form is. That's not the right word. What's the right word? It has jumped out of my head. I know what it is, I just don't know what the right word is.
Indeterminate?
Thank you. Indeterminate.
I think I was the one that said like indefinite last time and you said indeterminate. Is where you got that?
No, it's just senility setting in. So, we're interested in these when we're dealing with L'Hopital's rule. So let's go back, I guess we could cover password. We can cover L'Hopital's rule and indefinite forms altogether. So if you have some limit where you have something like this, x, g of x, or, you know, it could be different, but it's an indefinite form. What that means is that, well, as an example, the limit of x approaches c of f of x is equal to the limit of x approaches c of g of x equals 0. In other words, 0 over 0, which is an indeterminate form. It also could be infinity over infinity. It could be negative infinity over infinity. And there are a number of other forms that can be converted to look like this. So we could use L'Hopital's rule. They include infinity minus infinity, 0 to the 0, 1 to the 0, 0 to infinity, I think 1 to infinity is also one of them. They're just things that, you know, if you just evaluate it at the function, it's some number, we don't really know what it is, but the limit doesn't care. It just cares what are we getting closer to. So it's important always when thinking about using L'Hopital's rule to make sure you have an indeterminate form. Because if it's not, and you apply L'Hopital's rule, then it's not going to work. So L'Hopital says you have one of these forms, that this limit is equal to the limit where you find the derivatives of the two functions. Now, you know I'm repeating myself, but I want to make this clear. It's not the derivative of f of x over g of x, which would require the quotient rule. You just need to find the derivative of f of x and the derivative of g of x. So let me at least make up one problem. So what if f of x was e to the x minus x plus 1 squared limit x approaches 0. And what do we want to put on the bottom? Oh, that works. So we look at this and we see, well, okay, at 0, e to the x is 1. This is 1, so that's 0. And the log of 0 plus 1 is 1, which is 0. So now we want to know what this limit is. And L'Hopital says you can find the derivative here and the derivative here and reevaluate. So let's do that. So e to the x minus is 2 plus 1. And the derivative of the log is 1 over x plus 1. All right, now we again can check. Sometimes you might have to do this twice. Like if this is still an indefinite form, then you're stuck, but it's not going to be the case here. So what do we have here? We have 1 minus 2 over 1 over 1. Oh, negative 1. I just made that up. Came out okay. Again, you might, in the heat of class, you might want to check on your calculator. So come up in a second. Yeah, that's x plus 1. It's not easy to make up problems on the fly. Yeah, look at that. We find as x approaches 0, it's negative 1. So that's a good, good sanity check on your work if you're trying to see if, how do you check your work? Well, that's one way. And is there anything else on that sheet? No. Yeah. Oh, how to do an optimization problem? Well, this, like the related rates problem, it's just a matter of generating some function you want to minimize or maximize. And therein lies the problem. That generating that function usually involves some geometry, not always. So here's just an example I was thinking of earlier. You have x plus y is equal to 12. And, let's make it a little better. let's say we want to maximize x squared y. So that's some function we're going to maximize. This is easy because there's no geometry, but just, watch how it works, right? So I think what we want to do is get rid of y here, right? Y is equal to 12 minus x. This becomes x squared times 12 minus x, or 12x squared minus x cubed. And we want to find the derivative. This is how we find maximums and minimums. That's what we're doing, all in the beginning half of this session. So that's 24x minus x squared equals 0. Right? X times 24 minus x equals 0. So we know the minimums and maximums occur at x equals 0 and x equals 24. Oh, well, I did it wrong, didn't I? Thank you. 3x. So that's going to be where x equals 8. Thank you. See, this is what you have to do on yourself while you're doing the exam. You have to go, didn't I do that a little too fast? Does that make sense? Was I too nervous? Was I in front of the board? Okay, so if x is 0, we can do a little chart here. If x is 0, then y is going to be 12. And x squared y will be 0. That sounds like a minimum, doesn't it? If x is 8, then y is 4, and x squared y is 64 times 4. 64 times 4. All of you computer science people should take no more than 5 seconds to figure this out.
It's 128, 128.
It's very important for your future career as a programmer. 64 times 4 is 656. 256. The number of possible values in a byte with 8 bits. Okay. So this is obviously the maximum. Okay. So that's an optimization problem without any geometry. Yay! But take a look at that problem we did with that kind of window, was it? It wasn't an Anderson window, I think.
It's a radius window.
Radius window. Yeah, now this is the same thing, only with geometry. And you just turn it into some equations. We're trying to maximize the area, but we have some constraint here. So that's optimization problems. All right, any other review questions? Anything else to talk to students Ed about? Oh, I wanted to say a couple things. Of course you get a cheat sheet. Don't ask me again. No, you can't, but I'll just say the same thing. You get one sheet of paper, double-sided, anything you want to write on it. I'll bring some calculators, but do bring your own if you have one. If you need one, you can borrow one. What else? Yesterday, someone was trying to get me to say, how many questions? And I didn't know. But I don't have the exam finished, but I'm pretty sure there are 19 questions. So lots of simple little things to do, and maybe a few more involved questions. If you know the material, most of it will be pretty straightforward. Yes?
Were they going to do like an extra credit like last time? Or?
You want an extra credit?
I mean, just asking. I'm not gonna do it.
Right.
Probably not gonna do
Oh,
it.
you're not gonna do it? Does anyone do the extra credit? Okay, all right.
Just so I can like see what it looks like.
That's over.
You know, it's like you get, you learned it all and you get it done in an hour, you got an hour left. Why not? Work on the extra credit. Okay. Nobody worked on it, even worked, well, a few people just kind of,
I run it once.
a few people gave me an answer that wasn't really the whole answer. But, okay, I will put an extra credit. Don't panic. Study, put in your time, learn the material as best you can, do it, work with your friends. Send me an email if you have a question you want me to answer on Zoom. And get a good night's sleep, then come in refreshed and confident, and you'll do fine.
I have walkthrough.
All right, guess I've set it up. So, I'm sure everyone's more interested in, it's going to be more focused on the exam than on what we're going over now. So, I'm just going to give you the touchy-feely part of what we're going for, and then on Thursday we'll continue with a bunch of examples. This new section is 4.9 anti-derivatives. And I'm going to go back to my driving example. You're driving in your car down Route 5. You put the car in cruise control. And this is your distance. This is your time. Say this is, 70 miles per hour. And it's pretty clear, there's like 1 hour, 2 hours, 3 hours. In 1 hour, you travel 70 miles. 2 hours, 140. And in fact, the area under the graph here represents that mileage. Now, we could draw a graph of this. I'm sorry. I'm not doing this right at all, am I? Look at what I just said. This is velocity. Okay, now what I said is correct. 1 hour, 2 hours. So velocity is distance over time. This is time. And their product, which is the area here, is your distance. If we look at the distance graph, now we also have a straight line. This represents velocity, the slope of this now represents the velocity, distance over time, right? And if you think about it, if you're sitting in your car and you're not on cruise control, and instead of a straight line, you keep track of, well, we're going a little faster, slower, and we stop. If you kept track, you could break this up into little pieces. You could say over this section I went this far, and this section I went this far. And then your distance might, you know, I guess this represents, I stopped it for gas, because I'm not increasing my distance. Time again. So you can see, you can go back and forth between these diagrams. So it might be useful, since we know how to go from the distance function to the velocity by finding the derivative, it might be useful to go in the opposite direction, right? Knowing velocity, figure out how far we've gone. And that's what's going to motivate the rest of this semester, that idea. So let's just look at this mechanically for a minute. Let's say we wanted to do the opposite of what we've been doing when we've been doing differentiation. We want to go backwards. We want to find a function whose derivative is something. So let's start with a simple example, f of x equals x. And we want to know what function will have this as a derivative. Now, it's very common to refer to that function with a capital F. This is a small f function. This is our function where we're looking for the derivative of capital F is equal to f of x. So one might guess, remembering the way the power rule works, that maybe this is something like x squared. Would be a good first guess. Well, it's pretty easy to check. Find the derivative. It's 2x. Well, it's not x, but it only differs by a constant. Well, okay, that tells me if instead of f of x is x squared, I make it x squared over 2, the derivative will be equal to x. In this class, that's going to be the predominant way we're going to find antiderivatives. There are many, if you take Calc 2, you're going to go on with this, and there's a number of nice techniques for finding antiderivatives that we're not going to touch. Okay. There's one particular thing you want to watch out for here, though. Let's say I add some constant here. Well, this is also going to work, isn't it? Because the derivative of a constant is 0. We still get the same function back. Let's do one other example. Let's say f of x equals sine of x. And I want some function where the derivative of this function is the sine of x. Well, again, you might want to try cosine of x. We work backwards. That's the function. We find the derivative. The derivative of the cosine is negative sine of x. Okay, that's not quite what we want, but it differs by a constant. We put a minus here, we get a minus here, or plus, and then we now know that the antiderivative of sine of x is the negative cosine of x. Yes?
For the first example, do you not take derivative of 2? So you have f of x equals x squared over 2. Do you not take the derivative of the bottom? Because if you...
The 2?
Yeah.
Okay, I think what you're asking is,
wouldn't it end up being
Yeah,
x over
yeah,
zero?
that's, okay. This is a little bit off the subject, but it's a good intellectual question to ask. It's kind of tantamount saying, does this derivative stuff really work? Does it all fit together right? So let's say I have some function f of x, and I want to find the derivative of f of x, 1/2 f of x, which we're supposed to know is just 1/2 derivative of f of x. But you raise a point. What if we think of this as a function, right? We want to find the derivative of f of x over this function 2, which is a perfectly good function. Let's apply the quotient rule. Right? The quotient rule says this is f prime of x times 2 minus f of x times the derivative of 2, which is 0, over 2 squared. So what do we get? We get 1/2 derivative of x. See how that works? You don't have to do this. You can be confident that constants, you can just ignore them, leave them outside.
No, okay.
That was not your question? Oh.
No, I don't
Okay.
know. So you have x squared over 2,
Mm-hmm.
and so the 2,
Does it make any difference if I just call it 1/2 x squared? Does that make it easier to see?
so the 1/2, it doesn't,
It's just a constant. But we need that constant to get back to x, right? Let me go through the whole process one more time. We want to find an antiderivative to x. We know that the exponent is going to be 2. We find the derivative, it's 2x, which is not what we want. We don't want 2x, we want x. So we introduce a half here, and then we just get x. All right, I'm going to wrap up pretty quickly here, but first I'm going to go off on a totally, I think, another one of those fun tangents. Well, not mathematical tangents, the other kind. Again, something that if you can impress your friends and your family with. So, as I pointed out, whenever you're finding an antiderivative, you potentially end up with some unknown constant here. You can choose a constant if you have some more information, but this is we have a name for this. I'm running out of working. This is called a constant integration. So, what could be exciting about that? Well, you may have heard of this this eccentric fellow by the name of Albert Einstein, and he's known for a number of things. Most commonly is disappointing. Is two theories, one called special relativity and general relativity. has to do with gravity. And as it turns out, its theory is very important when you're studying cosmology, the study of the whole universe. Now, you may have heard that the universe is expanding. We look out and we see distant galaxies and they're moving away from us. And the further they are, the faster they're moving away. And its theory, is very important to this study. In particular, well, okay, so I'm not going to try and explain what this means, but his theory of gravity is summarized in a very odd-looking equation. It looks like this. That's kind of simple looking. This is actually, each of these little letters here represents 16 different variables. So this actually represents 256 equations, for which there's a lot of symmetry. There's really only 10 equations that this breaks down to. These are called Einstein's field equations. And they're used for all sorts of things, studying cosmology, studying black holes. This is how black holes were theorized, by looking at these equations. But initially, this piece of the equation was not there. It's a constant of integration. Einstein originally, he put in the constant of integration, then he said, nah, it shouldn't be there, it should be 0. That was a big mistake. Well, in 1998, it was discovered that the universe is not only expanding, well, if it's expanding and gravity is pulling it back, it should be slowing down. But in fact, we found it's speeding up. And at least mathematically, that's explained by this constant of integration. It's called the cosmological constant. We don't really know why yet. This fact that, things are moving apart faster and faster, we give it a name called dark energy, which my own feeling is it's a little premature to call it energy. There's some phenomenon going on, but cosmologists calculate how much energy it would take. It's not normal energy, because normal energy attracts itself, just like matter. This is negative energy, it's pushing us away. So that's really, that's all I want to say about this today. We're going to go over finding antiderivatives. Maybe we'll start on Thursday, doing it seriously. But just, I thought, interesting to connect this with things in the real world, things that are presumably in the real world. All right, that's it for today. I will head down to my office and hang out there till noon. And I'll be back at 1. Anyone, let me know if you're coming, so I don't miss you. All right. Who is it who wanted the extra credit? Yes. Did you see the announcement where I said, I think I didn't upgrade some people? Do you have, just send me what the upgraded score was. Send me your upgraded scores if it's not on the campus.